Okay, so here is continuation with class 11. This is video 3. We finally got to do some examples, and here is an example of a fire truck, this pumper truck, and it is delivering 1.5 cubic feet per second to from taking its suction or its input from a fire hydrant that's at 10 psi through a 4-inch diameter hose, and it's going through a pump that's inside the fire truck and going out through a hose and shooting up, and it's going up as high as 60 feet. If the head losses are negligible, right, we're saying if there's no losses between here and the pump, which is inside here, we'll draw like a little pump symbol, kind of a pump symbol right in there. We want to determine the power that the pump must add to the water, right? So it's the hydraulic power that the pump is adding to the water. And just so you know, this is not an electrical motor. What they do is they disengage the engine from the drivetrain in a clutch, right? Declutch, and there's what they call power takeoff. So the pump is actually driven by that same engine. There's a separate clutch that will clutch in, and a transmission probably to change the speed. So it's probably off of the same transmission, but they're able to put it into the pump that's inside, that's able to raise the energy up there. So it isn't just from the pressure from the hydrant. This thing boosts it up and shoots it up there. So just as a good to know type of thing, I think it's good to, they gave us to convert the units of the volume flow rate from 1.5 cubic feet per second just into gallons per minute, right? So 7.48 cubic, gallons per cubic foot. Almost got that backwards. And 60 seconds per minute. And so now we can see that this thing is going to go 673.2 gallons per minute. And that's really just a good to know. We don't need that. If we gave us gallons per minute, we would want to turn it into cubic feet per second. But I think this gives you sort of an idea of how much flow rate, because you can imagine a gallon of milk, and you can imagine how many gallons of milk that would be in a minute with a stopwatch, and that gives you a better idea of what that flow rate is going to be. One thing I do want to know, I want to know what the velocity is going to be right in there. So the velocity, and we're going to call that state, we're going to call this 1, right? So it's good to number these, and that's going to be 2. So we're going from state 1 to state 2 right here. So the velocity at 1 is going to be the volumetric flow rate divided by the area at 1. So that's that 1.5 cubic feet per second. And we're going to divide that by the area. We want to make sure we turn that into on a per foot basis, right? So we're going to take 4 inches divided by 12 and then square it. So what we're left with is 17.19 feet per second. And the units will work out right there because we're dividing cubic feet per second by square feet, so we should get feet per second. So we're ready to implement Bernoulli. And I decided to go with my equation that as I drew it, or I'm used to it. This is like Bernoulli 2 with the added stuff to it. So we go to the pressure at 2 divided by the specific weight plus the velocity 2 squared divided by 2 and the acceleration of gravity plus the Z2, right? So this is the elevation. P1 divided by specific weight plus V1 squared divided by 2 in G, and then the elevation at 1. And this time we're going to add pump head to this, and we're also going to include the losses right there. So there's our Bernoulli 2 with the addition of outside influences. Here we have a pump, and we also have losses. We can start crossing things out based on what our scenario is. We could see first off that we're going to start right here. This is the datum. It's a good idea to treat that as this datum. So we will take, and I'll get rid of that. We're going to at state, well, actually maybe I'll go up to here at 2 right here. This is going to be at the atmospheric pressure. We're also going to go up as high as we can. So we're going to say the velocity goes to 0. This height right here, that's going to be equal to the 60 feet. The pressure 1, that's going to be what's happening right here inside this. We know what the velocity is. We just found it up here at state 1, so we're good. And like I said, this is the datum. This is what we want to find. And they said if head losses are negligibly small, we could go ahead and say that these are negligibly small. So we're ready to put stuff into here. We take this, and I'll say this is 60 feet. It can be equal to 100, no, excuse me. Sorry, get this right. This is 10 psi. PSIG, by the way, that's why we can go atmospheric right here. So it's going to be 10, but let's go to 144. So we turn it into pounds per square foot and divide it by our specific weight of water, 62.4. I don't know why I started writing the wrong way. So anyway, that's going to get, this is the pressure head, static pressure head. And then we're going to have our 17.19 squared divided by 2 and divided by 32.2. So that's going to be our dynamic head coming in. And then this pump head that we're going to add to it. And so from that, we'll have a pump head that's going to be equal to 32.33 feet is how much pump head we're adding to this. But we would like to have this in power. So the pump power is going to be HP gamma and the volumetric flow rate, or 32.33 times 62.4 times 1.5, right? And you might want to take a look at the units right here. We have, let's see, we have feet times cubic feet per second. No, pounds per cubic foot. What am I doing here? Pounds per cubic foot. That's that guy. And this guy is going to be cubic feet per second. We can see those cancel out. We get a foot-pound per second. So here's our power. Comes out to 3,027 foot-pounds per second. But I don't know what those are, but I do know what a horsepower is. And so we can divide by 550 foot-pounds per second per horsepower and come out with 5.503 horsepower. So this is the delivered horsepower of the pump. So this is pump, and I guess if we're going to use the subscripts that they've been using in the book, we'd say it's 5.50 horsepower. And maybe you've owned a lawnmower that was 5.5 horsepower, maybe. That'd be a pretty big lawnmower, I think, for the most part. Doesn't have to be. I think I have this Briggs and Stratton engine. No, it's the Harbor Freight engine. Sorry, the Harbor Freight engine. I think that's 5 horsepower. Yeah, so it's a decent size. Not huge. But this is the useful work, right? This engine. This is the output from this engine, right? So if you want to say, well, how much engine power are you taking? Well, I don't know. Most engines aren't going to be more than, say, let's go engine efficiency, is usually not going to be some more than like 60%. You're not going to do much better than that. You could argue about what kind of engine and that type of thing. There could also be transmission losses, other things. So like if you were to say like the engine power that you'd have to out of this, what you do is you have to divide this one by that efficiency, by the engine efficiency. So this is just for example. This wasn't part of the original problem. And I don't know why I had put an E on 4. I'm going 4. Yeah, I go 4. 5.5, 3. Put the other in there. divided by 0.6, right? And maybe you get something along the lines 5.5, 0.6 divided, and you end up like 9.17 horsepower, right? So you have to have, we need to have an engine that's capable of doing that to be able to generate this useful work, right? So this is like hydraulic power, and this is actually how much that maybe that has to go in from the engine. So that's the first example. I'll do another 2 examples. So this was video 3, right?